Hi, welcome back. In the previous lecture, we look at how to combine a single qubit state to form a two-qubit system. In this lecture, I'm going to describe the transformation acting on a two-qubit system that corresponds to two-qubit gates. A two-qubit quantum gate is nothing else than a 4x4 unitary matrix. Remember that any quantum gate is expressed by a unitary matrix which has two properties. One is reversibility, and the other one is to preserve the norm. So this 4x4 unitary matrix will act on a quantum state of the two-qubit system that we saw in the previous lecture consists of four complex values organized in a four-dimensional column vector called cat. The way that we construct these 4x4 matrices is the same way that we use in combining quantum state by taking a tensor product. So we construct such two-qubit quantum gates using the tensor product of two one-qubit quantum system. So let's look at an example. So we have a two-qubit system that correspond to two wires, and then we have a U1 that is a quantum gate acting on the first qubit, and the U2 acting on the second qubit. And then we want to determine what is going to be the state after this transformation. So this transformation will occur in parallel on two different qubits. So we can have a two perspective. The first one we can apply if we have our quantum state 1 and quantum state 2. We can do two things that are equivalent. The first one, we can apply U1 to the quantum state psi1, and that will be the results. The first one, and then the second qubit will be also transformed. There will be U2 acting on the state of the second qubit, and this will give the results for qubit 1 and qubit 2. And this will be a two-dimensional complex value vector. If we want to have the combined state of our two-qubit system, we will take these two guys and take the tensor product. An equivalent way will be to do this. And so we can take the tensor product of these two vectors, psi1 and psi2, and this will be the combined state of the two single qubit. And then we can take the tensor product of these two matrices, U1 and U2. And we applied this tensor product of these two gates, single qubit gates, to the combined state of the qubit 1 and qubit 2 as an input. So this formula you see here is nothing else what I just described now. So if we take the tensor product of the two qubit state and we applied the tensor product of the gate, this will be equivalent to apply the single quantum gate to the single qubit, and then after that combine with the tensor product. So we saw in the previous lecture how to combine vectors using the tensor product, and these slides present how to combine matrices by using tensor product. So this is very similar to what we've seen before. We take each element of the matrix A1, and then we multiply for the full matrix on the right side. In this case is going to be B, and we do by element. So we take A1 and then we multiply element by element for each matrix, then A1, 2, and we multiply for the matrix A2, 1 here, and we multiply by this matrix, and A2, 2 multiply by this matrix. Then the next step is multiply element by element, and we unroll and we got like 4 blocks. So whenever we need to combine two gates that are single qubit gates acting on parallel, we can use just this tensor operation. So we take the matrix formulation of each gate and we multiply by the tensor product. So the tensor product of the gates occur when we have a circuit with the two qubits and a pair of individual 1-qubit gates. So in this case here, we have two gates, X gates, acting in parallel on two different qubits. So what we're going to do, form the combined transformation on a 2-qubit system into the tensor product. In many cases, you see the following case, that we have a gate acting only 1 qubit and nothing on the other one. So in this case, it is implicit that there is an identity matrix. So if we want to calculate what is the combined transformation on the 2-qubit system, we take the explicit gate and we multiply by tensor product by an identity matrix that is implicit. So far, we have seen how to combine one single quantum gate to another one single qubit quantum gates. But there are many unitary matrices that cannot be written as a tensor product of other simple matrices. So the most important one is the so-called control NOT or control X gate, usually called C NOT, stands for control NOT, given by the unitary matrix that has this structure. So we can divide it in 4 blocks. You see identity matrix here. Then you have here what we call X or NOT gate, and the rest aside the diagonals are all 0. And this is the symbol for the C NOT. So how the C NOT gate works? Well, in order to understand how this works, we need to write here the values for the qubits. So if we have this is a 4x4, so it's acting on a 2-qubit system. And if we put 0, 0, 0, 1, and 1, 0, and 1, 1. And then we do the same for the row, so 0, 0, 0, 1, 1, 0, 1, 1. So this is the input. So we see that when the first qubit is 0, the output remain the same, right? So this is just an identity matrix. When the first qubit is equal to 1, the effect of the C NOT gate is to flip the values of the second qubit. You see here, this nothing else than X. So if you see, for instance, C NOT, when the first is 0, the output is going to be the same. When the first qubit is equal to 1, then this is going to flip. The value of the second qubit is flipped if and only if the first qubit is 1. In other words, the application of a NOT gate on the second qubit, the so-called target, is controlled by the first qubit. The symbol for the C NOT gate is the following, where we have the NOT gate on the target qubit. So in this case is the second qubit is the target, and then this field dot is the control qubit. In some cases, we have some technical difficulties restricting the number of C NOT gates, or which qubit is the target, which one is the control qubit. So we can use gate equivalence. For instance, in this case, if we have a situation like this one, where the control qubit is the second qubit, then we can express this with this equivalent form. Let's say that we have only this kind of C NOT on the machine. We can implement this other C NOT gate where we swap the control and the target by using this equivalent circuit. This is the last slides. I just want to say a few words by an important gate that is called the swap gate, that is used to interchange or swap the states of 2 qubits. So you will find, for instance, in the quantum Fourier transform, at the end of the quantum Fourier transform circuit, this is very much used. Also used by compiler to transform the quantum circuit, and this can be obtained by a cascade of control NOT gates. This is the last slides, and talk to you soon.